Welcome to another series of video lecture. In this video lecture, we'll be looking into one type of experimental design, randomized control design, or RCD or RCT. Randomized control design, RCD, or a randomized control trial, RCT, or randomized complete design, RCD, randomized complete trial, RCT. So you may be coming across any kind of name, but in short, RCT or RCD are quite common names. These are the most simplest type of experimental designs. Sometimes you may come across one more name for it, um, OFAT method, one factor at a time. So you'll be keeping one factor as a variable, rest all as the constant. So this forms the basic model. Now, as we have seen in the previous video lecture, we have come across factor, we have come across uh, levels, we have come across response variable, we have come across design space or region of interest. So just revise those particular topic contents. Now here in this experiment, we have only one factor to be varied at a time. Most important thing is the experimental units what we take, means each experimental component we take should be homogeneous. That's most important aspect in this experimental design. Homogeneous in the sense, each experimental block that you take, each component on which you do the experiment should not be varying from one another. So all should be similar in type. Only something that varies is your treatment in the sense the level that you have applied changes, rest all otherwise it should be remaining same. I'll give an example of that once I tell you what is this treatment and levels. Now let me say that you have taken one factor, there is no other factor varying here, only one factor we are varying, and the treatment levels for that are T1, T2, T3. Now you can vary only one factor at a time, all other factors are constant. So you have one factor varied and the level of that is T1, T2, T3. That means 3 level you have taken. At each level you will be performing experiment. Now experiment number 1, Y1, experiment number 2, Y2, experiment number 3, Y3. For all this you have varied at T1. At a T2 you performed the experiment 3 times. So you have just repeated it 3 times. At T3 you have done experiment 2 times. You can observe one thing here. Here 3 samples are there, here 3 are there, here 2 are there. For our analysis purpose, minimum 2 experiment you have to perform. Minimum 2 experiment you have to perform so that you can do the ANOVA. At least 2. Minimum 2 you have to perform. Otherwise you may not be able to identify the variations. So the number of sample total here is 3 plus 3 plus 2. That is 8 experiment you have performed with 3 factors. So you can have any particular order. Most importantly, it is one factor at a time. The meaning of this one, I'll just take one example here. I want to test the efficacy of a drug. What I will do is that particular drug at 3 different composition I want to test it. 3 different composition of that I want to perform, test it, clinical trial, preclinical trial. So I'll be using mouse as the animal model for my experiment. What I've done, I've taken 8 mouse number 1 to mouse number 8. The meaning of homogeneous experimental unit in the sense, all 8 experimental units what I've taken, all 8 are experimental unit now. All 8 should be homogeneous, means whatever is the characteristic property, whatever you have health condition or whatever you mention about mouse of mouse 1 should be same for 2, 3 up to 8. All should be homogeneous, almost similar in nature. There shouldn't be variation among them in their health condition. One is very young, another is very adult, like that kind of variations you should avoid. So you try to take almost same type of 8 mouse. So that is the meaning of homogeneity. Now you will take for this thing 1, treatment 1, you will be taking dosage 1, dosage 2, dosage 3. You will perform the experiment and you will do the analysis. Now this result, the result may be increment of some blood composition. Some result will be there anticipated as some improvement in some health condition, or it could be increment in particular chemical in the blood. So some response variable will be measuring as a result of this. So that result you will have to identify, and that will be your y. Now you can prepare a model in the sense you are done the experiment. After experiment is done, you will be converting it to mathematical formulation, one mathematical equation. The response is y. This is your response. Now there are 8 samples. All 8 samples have their own value, individual value. None of them are same. Now if you take the average of that, that means you got mean. Let me say that you got mu. This mu is the mean. Now if there is possibility that all 8 are not same, the reason could be there could be natural variation. Forget about your T1, T2, T3. You have to varied the dosage forms. I'll keep it aside now. Y1 to Y8, there is response is not same. Maybe because there is a natural variation. Because of natural variation, all are not having the same value. That is why all are not having the same value as mu. There is some variation. That is our natural variation. There is epsilon. But these values may be further away from this epsilon. Mu and epsilon may not be within that range. So that extra variation what you have, that may be because of this treatment. The treatment might have caused the value of y1 further away from its individual value yi. Say for example, the mean is the individual values are varying from 10 to 20. Let me say that the 8 values are varying from 10 to 20. The mean is 15. The average of all these 8 values is 15. So you expect all the values supposed to be 15. Not so. It is starting from 10, varying up to 10. So you expect that it is at 15. All these y responses are 15. No, the value is not 15. Now you expect that there is some error. Okay, I'll take the standard deviation of that whole set of values. When I check the standard deviation, the value standard error in fact, so epsilon is the standard error. So when I check it, it is supposed to be from mean is 15, supposed to be from 13 to let me say 17, 13 to 17. All the values are supposed to be within 13 to 17. Now this particular y2 or y1, y2, y3, I see that all these values are somewhere like 18 to 20, 18, 19, 20. These values, they do not fall within the 13 to 17. So you are expecting that it is supposed to be within 17 if it is natural variation, but not so. It is going above 17. It is maybe 18, 19, 20. Why it is 18, 19, 20? Whereas these things are very low values. They may be 13, 14, 15. This may be 10, 12. So why this is very high? Maybe you have used one particular dosage that may be causing this particular increment in the value above the epsilon, that is mu plus error, that is beyond the natural variation. So that may be telling you this is significant or this may have significant effect on that. So that kind of analysis, not it's not, this is just a qualitative explanation I have given to you. So what it shows is variation in errors, that is from the mu it is moving away. Why it is moving away? We are introducing one term tau. The tau is nothing but because of the treatment there is some variation. So your yi will be equal to mu mean plus variation because of tau. You can note that mu I and mu I same here. This mu I, replace it here. So this equation becomes yi is equal to mu plus tau I plus epsilon, means each value will be equal to gross mean plus variation because of treatment plus natural variation. So there are 3 terms involved here. One because of your factor what you varied, another because of natural variation, over and above the gross mean. All are supposed to be gross mean. Now to analyze it, we will be using analysis of variance, ANOVA, which is nothing but F test. So you will be using F test for all design of experiment, analysis of design of experiment. Now what exactly we are trying to do here? We are checking for the treatment versus error. Treatment versus error we are comparing. That means we are comparing this tau versus this epsilon. Question is simple, whether the variation because of the treatment is greater or the natural variation is greater. I told you 13 to 17. 15 is the gross mean, 13 to 17. If there is no effect of all these things, all values would have been within 13 to 17. So the ratio would be this epsilon will have upper hand compared to tau. If majority of the values are beyond the 13 to 17, this tau will have upper hand compared to the natural variation. So who is having the upper hand? Treatment or the natural variation? We are checking it. So if treatment is having upper hand, you already come across ANOVA, that's why I'm just going ahead with this. So you have the treatment having higher value compared to the error. That means this F value will be very large. That means treatment is having very significant effect. If error is very large compared to treatment, mean square errors if I say, so this F value will be lower for that case. So natural variation, so you will be say insignificant. Treatment is insignificant. There may not be effect by that particular factor. Now coming to the degrees of freedom, just keep an eye on this degrees of freedom in the further design of experiments. Very simple one. So always the total number of experiment what you conducted, including duplicate, triplicate, whatever it is. So it will be n minus 1 is the total number of degrees of freedom, n minus 1. So if you have conducted around 6 experiment with the 2 factor, you have taken 2 factor and 6 experiment. That is the case, 6 minus 1, 5 is the total degrees of freedom for that. For the treatment, number of one factor, 2 levels. For 2 levels, t is the level. You have taken 2 levels, 2 minus 1, 1. Treatment is having 1 degrees of freedom. 2 levels, 1 factor, 2 levels. You have taken only 2 levels, and you have done 6 experiment. In that case, 6 minus 1, 5 here. 2 minus 1, 1. Rest will go to the error, degrees of freedom of the error. So you perform total minus treatment. First find out how many treatments are there, then you find out how many experiments are there. So t minus 1 for the treatment, n minus 1 for the total. So this value minus treatment degrees of freedom all gives you error. So don't directly calculate the error, instead calculate this way, total minus treatment degrees of freedom. This experiment has got advantage as well as disadvantage. The biggest disadvantage is in this case the sample has to be homogeneous. The experimental component should be homogeneously distributed. Advantage is it is very simple to construct and simple experiment. You can work out with only one factor in this experiment. So this is RCT or RCD. Thank you.